Lucky number 4. It was fast, but it wasn't like. Well, you have to turn left across like 6 seconds of traffic. I mean, you have to go fast. So.
Just throw it back on my binder when you're done, Tom.
Why? Get it?
Hi. How are you?
Hello, welcome.
I've already done you for a second.
Yes.
Oh, second's up. Sorry.
Oh.
Okay,
You know what? I can talk fast. but
Yes,
not
you
quite
can.
that fast.
look at the water gallons. Ooh, they're multiplying.
Yeah, right.
Chris's doctor said he should drink more water.
That's probably a good idea for all of us, honestly.
Why is the flower going sideways?
I don't know, I'm not sure. I'm not responsible for the flower, you guys know I can't draw squat.
Like, sure, drink a lot of water.
Okay,
You think I can make that?
so,
Looks like you get it far away.
I'm gonna bring that one around. I love that.
okay. Now, you guys have to tell me, do we need to review 3? That would be from the homework number 3. Okay. So, number 3, finishing up yesterday, hopefully we're moving on and Okay, so the function for number 3, is 2x plus 3, and it says we're supposed to do the area between 0 and 6. I think I've said this to you multiple times before. I would get in the habit of going ahead and sketching the region, because when we get to what we're going to do next with this stuff that depends on this, it will be of use to you to be able to sketch it, because what we're going to do is be taking areas that we normally used to find and rotating them around different axes and doing different things with them. So it should be the case, notice again, I'm not using the calculator, that you guys are able to sketch y equals 2x plus 3. Just like people in Algebra 1 can sketch y equals 2x plus 3. What kind of thing is it? It's a straight line, there we go, and so it goes through 3, and its slope is 2, and I'm just going to wing it and go, okay, the graph looks something like that. Are you alright with that idea? What's that? That's not too bad. I don't know if the slope's really 2, but we'll just wing it for right now. It says the area that we're interested in is from 0 to 6. Now, I did not plot this exactly. What I typically have a habit of doing is kind of just shading in this region right here and saying, okay, that's what we want to try to find. Okay? Now, I haven't, I don't think I need to go any further. Caps are falling. This is one black marker cap that always keeps falling off. Not sure why. Alright, so, on your papers, you have delta x. And what did you put for delta x? Since Isaac asked about this one. You put, other people are answering for you, 6 over n. Do you know where that comes from?
Yes.
Got it. Okay. And then the next thing that's on your paper, guys, is right-hand endpoint, which would be, in this case, 0 plus 6 over ni. How am I doing so far? Okay. Now, beyond that, it says find the sum, find the area. Calculate it using the method that's up above. So our little expression needs to start with limit as n goes to infinity. The sigma, you guys have seen this now for several days. Oops, this goes to n. Now, we're going to sum, obviously, f of the right-hand endpoint. That's how we find the heights. So this means 2 times the right-hand endpoint. Is it okay with you guys for the right-hand endpoint, Isaac, since you asked me about this one? If I just put 6 over ni, because 0 plus 6 over ni is going to be the same thing. And then I have some space back here because my function when I plug it in is 2x plus 3. So I'm plugging this in for x, and then of course I need to multiply or put a dot right there times the width of the rectangles, and the width of the rectangles is delta x, which is 6 over n. So you're seeing me plug, yes, sir?
So delta x is never being, summation.
It's no, well, it's multiplied by that. Like, every time we do this, this gives you the height of the rectangles times the width of the rectangles. Like, this little expression right here is the area of one rectangle, which you're going from n equals 1 to infinity. So that's how we find that. And we find the height by doing f of the right-hand endpoint, plugging it in, times the width of the rectangle. Which, wow, let me just do it this way, times delta x. And delta x is up here, and the right-hand endpoint is over there. So that, you are absolutely correct. When we do this little sigma stuff, you guys remember this, normally what I do then is go, okay, this 6 over n, we pull it out in front. That's kind of what you're talking about, I'm assuming? Yes, that's definitely gonna be the case. Okay, so let me go ahead and do this. You guys are used to seeing this. Now, it's okay, hopefully, if you guys are, agree with this. If I just multiply this, I'll put this in orange because this is the thing that I'm doing a little bit here. So this is 12 over n times I, and then plus 3 stays where it is. Am I doing okay, guys?
Guys, forgot the 3.
You forgot the 3.
I was looking at the second one.
You know what, you just have to be super, super careful with your algebra. I can stop if you guys are okay finishing this, or I can continue going. It doesn't matter to me, I'm happy to do either way. These are real tedious algebra problems, so I know that they're like, sometimes confusing and you might get the wrong answer, just because,
You still finish it.
yeah, sure. So what should we do next?
Use the formula for I.
Yeah, I would actually split this up and do, this is 12 over n times I, and then this is, you're summing 3, and all of that is there, and you still have the 6 over n, and you're taking your limit, but you're absolutely correct, like you need the formula for I. So if you guys want to take the time to write that in front of that, you know what I mean? Because the 12 over n ends up being just a coefficient. So I probably ought to do that with orange, but I haven't. So you say keep going?
Yes, please.
Okay, so we're going to still write the word limit as n goes to infinity. Now, if you wanted to, excuse me, we could keep the 6 over n where it is, and then big set of parentheses. So the 12 over n could have come out in front, and then we need the formula for I. And the formula for I was 1/2 times n plus 1, so I'm plugging in that. And then when we do the formula for summing 3, and again, my street calculus here is probably pretty bad. What I mean by that is this. I should be a little bit better, guys, about this. I would do from I equals 1 to n and I equals 1 to n. What I was getting at is I was splitting those things apart. Okay. So you are absolutely right. I need the formula for how to sum I and the formula for how to sum 3, which is just 3n. Now, are you okay finishing this? Because now we just, okay, you're finished. You're good finishing this. Okay. Unless other people need help with it, I'll stop there. If you need me to keep going. And again, the answer number 3 I ended up with was 54. So a lot of algebra, more than anything. And that's the headache part, right? You have to be super careful about all the little teeny tiny exponents and make sure you don't forget the 3 like something I would do. Or you've seen me do problems where I'll forget to multiply by the width of the rectangle, which is really stupid because you can't find the area of a rectangle without height times width. Anyways, yes.
No.
No, you're stretching. Okay, got it. Now, as I mentioned to you all before, hopefully we'll be in agreement with this. Shut up for a second. To give you an example of where this is gonna, how this is gonna come into play. Like, are they gonna give you a problem like this? I highly doubt it, but I'll explain to you how it's gonna show up. So do you have any others in the homework stuff that you'd like to ask about before I show you like how this is gonna go down? Like, let me give you an example of what's gonna happen. Now, if I were you, I would put this on some piece of paper. You probably don't have any room on this. But just to give you an example of like, where does a Riemann sum show up at the stage that you know it right now, before we get to calculus, because that's what I want to take you into. But let me give you guys an idea of how this is going to work. Okay, so here's a little example. You might want to jot some notes down on this. This is going to be the speed of a car that starts from a stop. And you're like, what in the world? You've been giving us functions so far. And every one of these I've done with you so far, we've had functions, right? We've had like the y equals. So what I'm going to give you here is a little table. And t is going to be in seconds, and the velocity is going to be in feet per second. And so this is how these kinds of problems are gonna show up. 0, 2, 4, 6, 8, 10. And then over here, 0, 4.5, 6.9, 6 was 8.8, 8 was 10.4, and this is 11.9. Now, let me explain to you, and watch this carefully. If you're not paying attention, I would pay attention. Because this is where you're like, oh, maybe doesn't look the same, but I promise you it is, okay? So sometimes you're given data in a table rather than given an equation. This is the first time you've seen one of these kind of problems. So they're gonna give you some information, and what they're gonna ask you to do is, how far has the car traveled? So let me put this is the question that we're gonna answer. And you're probably thinking, how far has the car traveled? How in the world am I supposed to be able to figure this out? Let me help. We're gonna do this by sketching it. Now when I say sketch it is a pronoun that just means the data points here. We are not, listen to me carefully, we are not connecting the dots because they didn't give us a function that we're gonna sketch. Are you with me there? Not gonna connect the dots. I'm not gonna draw this completely exactly. Let's just do this. Let's go ahead and put like 11.9 up at the top because clearly that's the biggest y value. Okay, and then let's put some other numbers on here. The next number was like 10.4, so I'll just do that. And the one below it was like 8.8. The one below that was 6.9, and then 4.5. So just stick the y values on there. They don't have to be perfect, okay? It's totally fine if they're not perfect. Now I will tell you, oftentimes when we do one of these kind of problems, although I didn't do it here for you, the X list, or the T list in this case, might not be numbers that are evenly spaced apart. Okay, there might be numbers that are like 1 to 5, and then 7, and then 28. But for right now, we'll just stick with one that's the same, like, gap each time. Okay, so take your time. Now, on the x-axis, let's go ahead and do 0 to 2, 4, 6, 8, and then 10. Now, please label these. This is feet per second. Seconds, and this is seconds. Now I want you guys to tell me just for right now for a minute here, if you took feet per seconds, or per second, times seconds, just the units, what would happen if you did the units feet per second times seconds? You would get feet. Now, this is obviously that thing that 80-mile-per-hour video woman cannot figure out, right? Okay, but you do, you understand this. Now, here's what I want you to do. We're going to plot the points. 0, 0, let's plot our point. 0, 0. 2, 4.5, let's plot our point. We're not connecting the dots. 4, 6.9, 6, 8.8, 8, 10.4, and then 10 was 11.9. Now, it might look like mine's a straight line, but again, if I plotted this with actual y values, like put all the hash marks in, it's probably not going to be a straight line. You guys can tell clearly here that's a difference of 4.5. That's not a difference of 4.5. Do you know what I mean? This is not a straight line. Do not expect this to be any kind of curve, and do not expect us to try to find the curve that goes with it. We don't care. We're not going to do regression. There's probably not a function that makes this work. Because in this case, someone was just measuring a car at a stoplight, and they took the speed at time 0. Obviously the speed was 0, the car was at a stoplight. 2 seconds, 4 seconds, all the way up to 10 seconds. So they might have just used a radar gun to try to estimate the velocity or the speed of the car, okay? So here's how this works. The directions are going to say, and maybe not, but they're going to say, find how fast the car, or how far the car has traveled. Do you guys see that when I take the units, the y values, feet per second, and multiply by seconds, I get feet. Isn't that distance? Isn't that how far the car would have traveled? Okay, so here's what we're going to do. We're going to use Riemann sums. We're going to take this function here, and we're going to be doing this. I want you to draw the vertical line here down to 2, and the vertical line here down to 4, vertical line down to 6, vertical line down to 8, and the vertical line down to 10. Now, I'm not connecting the dots, because I don't know what kind of curve, and likely there isn't a consistent curve. We don't have enough information to connect the dots, because we don't know how fast the car has accelerated. The velocity is changing with acceleration. You know, it's not physics, it's just calculus. So we've got something that's weird, different here, because we don't know what the curve does. We don't care what the curve does, honestly, because what you've been doing with me recently is finding rectangle areas, right? Okay, so here's what we're going to do. instead, we could use left-hand endpoints or right-hand endpoints, it really doesn't make any difference. But I want you to take a look at this and think, we're gonna call this area 1, area 2, area 3, area 4, and area 5. And you're like, how are those areas if you don't have a curve up above? Well, we're gonna just estimate the rectangular areas using the right-hand endpoint. So do this, go over here and make that a rectangle, make that a rectangle, go over here and make that a rectangle, and that a rectangle. So we're gonna be estimating. We're not gonna find an exact answer, but we can get an estimate by making this area into rectangular shapes. 5 of them. Are you okay with that idea? Okay. So for each of these, for every single one of these, I want you to look at area number 1 and realize that area number 1 is a rectangle. Do you guys agree with that? Actually, all 5 areas are areas of rectangles. So I want you to think of this. This means 2 seconds. On the x-axis, it's 2 seconds wide, right? And the speed is 4.5 feet per second. What I want you to see is that if you look at the units, doesn't that give you just feet? See that? By finding the area of that rectangle, we've now found a distance. See that idea there? That's what we want to do for each one of these. So this is the first one. For the second one, I probably don't need to do the units. I think you get the idea of the units for each one of these. Okay, for the second rectangle, we're going to be using the distance of 2. So it's always 2 seconds times, we're using the right-hand endpoint, which was 6.9 feet per second. 2 times 7 is 14. So this, I think, is 13.8. You guys tell me if I did that wrong. But I think that's right. Sorry. Okay. Area 3, again, would be 2 seconds wide times the speed of this right-hand endpoint was 8.8. And that's feet points. Thank you. What did you say? You're awesome. 17.6. Strong. And then area 4 would be 2 seconds times 10.4. 10.4. We should have used my units. Feet per second, which would be 20.8 feet. What am I doing there? Good. So just basic arithmetic. We don't have that summation stuff is crazier than this. This is better, right? Not it. This is way better. Okay. So then 5 again would be 2 seconds times the last type was 11.9, and that was the velocity, it was in feet per second. 2 times 12 is 24, so this should be 23.8. Okay, so all we need to do is add them up. Add up the number of feet covered by estimating the first rectangular area. It's an estimate, it could be off, because we don't really know, guys, if the curve goes like over or do you know what I mean? We don't know. It's an